Okay, let's make a little comparison to see if we can solidify this information, all right? So we want to compare the standard normal distribution, Z, of the T distribution, all right? So we're looking at my Z and my T to see the difference between these two. So we're using just statistical software in order to come up with these histograms and so we can make these comparisons, all right? So this... Let me make this as big as I possibly can so you can really see these numbers because that's what we want to talk about. This is a histogram of Z, sample size, a histogram of T with sample size 5. Same sample size. This one's just a T and this one's just Z, right? It's the exact same sample size. So that's what we're looking at between those two. Okay, so if I have, oops, I lost my train of thought. My Z-score, look at these values. Man, how did I make this bigger? I don't know. Can you see this? I'll write it bigger. -3, 3. And here, if I'm looking at these values, this is bringing it here at this -10 and 7.5. Do you see what's happening? Let's just go with -7.5. That does go down to 10. However, I mean, there's very little data down there. So you can see what's actually happening here. So you can kind of see how they play out, right? Okay, so look at what's happening. Are they both bell-shaped? Yes, right? We can see that. Both of these are bell-shaped curves. They are shaped a little bit differently, but they're both bell-shaped. But what is the difference between these two? When Z is equal to 5 versus T, or N equals to 5 with the Z distribution and the T distribution, do you see what's happening? Okay, so both of them are centered at 0. Nailed it. But these numbers are the key. Both bell-shaped. If I'm looking at my normal, I'm going between -3 to 3 because that's the normal distribution. But this is what old Gossett was looking at. Oh, okay. Well, then this has a bigger tail and it's making a difference here, even though my sample size is the same, or that N, right? Okay, well, what happens if I change up that sample? What if we're looking at this 10 here? Here I've got Z again, but N is equal to 10 with my Z, equal to 10 with my T distribution. What do you see right here? Well, you can't see anything because it's too small. Maybe you can see it better on your papers. 3, 3. Ooh. What are you seeing? Still bell-shaped, right? And then this one, because it's normally distributed, because of this Z, I'm still going from -3 to 3, even though I changed it up, because it's a normal distribution. You have your mean. You have certain numbers of standard deviations that come away. But look at what's happening here. My dip varying, still a bell curve, but my variation is different. I'm going from -4.5 to 4.5. When your sample size changes, it changes the variability. If it's normal, then that's why we have that generic normal where my mean is 0, my standard deviation is 1. That's the normal distribution. If you don't have that, sample size makes an impact. And that's why we talk about degrees of freedom, because it's going to be different depending on this sample. And that's what that William Gossett figured out. All right. He figured out this is how things were changing. And that's why we have this T distribution. Based on this, and so you can see how this is playing out. Based on this, we now have these different properties that we can glean for the T distribution. I just wrote all over that. The T distribution. All right, because it is a little different. So we have to treat it different. And we talk about it different, right? Okay, so here are these 6 properties. The T distribution is different for different degrees of freedom. We literally just saw that. The T distribution is centered at 0 and is symmetric about 0. That's what makes it a bell curve here from 0. Okay, the area under the curve is 1. still the same, right? The area is still 1. That's the same thing that we were dealing with previously. The area under the curve to the right of 0 equals the area under the curve to the left. I'm going to squeeze this up. So here at 0, that means no matter what this looks like, the right side is half, the left side is half, and then those are equal. All together is 1. Same thing that we already know with the bell curve. So that's not brand new information. That's just bell curve information, right? Let me see if I can make this a little bit bigger. As t increases or decreases without bound, the graph approaches but never equals 0. Down to here, super close. Down to here, super close. That's what they're saying. Doesn't go under. Oops. Can't go under. Can't go under. Can't go above over here. It has to go towards 0, gets infinitely close, just like our other bell curve. So these two pieces, they're still bell curve info. The area in the tails is a little greater than the area in the tails of the standard normal distribution because we're using S as an estimate of sigma. So we're using the sample standard deviation as an estimate of the population, thereby introducing further variability into the t statistic. So there's just more variation right here, and that's what it's talking about, which we just saw again, right? We just saw that. How varied, how spread out, how tight is this to my 0? That depends on whatever your sample is. As the sample size increases, the density of curve t gets closer to the standard normal distribution curve. All right, so this is the normal up here with this kind of like a teal color. So as this gets bigger, we get closer and closer to the normal distribution curve. This result occurs because as the sample increases, the value gets closer to the value of the sample gets closer to the value of the population by what? There it is again. What did we say? What have we always said this entire semester? The more data you have, the more accurate it is, the closer it gets to the normal distribution. Mic drop, right? Boom. Here we are, literally saying the same thing, right? I say this all the time. Pete and repeat, we're in a boat. Pete fell out, who was left? Repeat, right? Pete and repeat, we're in a boat. Pete fell out, who was left? Repeat. We're just repeating ourselves over and over again because this is a key concept in statistics, right? However, when it is not huge numbers, when I don't have those big numbers, what was our key? 30. Yup. So if it isn't that 30 situation and we're going below that as we're working with some of these, then that makes a difference. It also makes a difference because I'm talking about a mean and I'm working with mean here. All right. All right. So, oops, I'm going to scroll this down. I want to point out here that I lost it. So this is exactly the same. It approaches but never equals 0. There's that variability there. Okay. So no, we're all good there. Now here is a chart. So I want to make sure that you understand what this chart is, just because we're going to look at it, just so you have an idea. We're going to find the t value such that the area under the t distribution to the right is 0.10. So that's what we talk about here. Assuming 15 degrees of freedom. If I have 15 degrees of freedom, what is n? 16, right? Because degrees of freedom is n minus 1 equals your degrees of freedom. Okay, so I don't need to know that other than the fact that if I'm already given the degrees of freedom, then I don't have to look for it. So in this particular problem, whenever I have those values, we're going to look at our table. And that's the last page of these notes. So right here, our t distribution, here is my 0.10 because that's what it had there. And I have 15 degrees of freedom. 1.341. All right, that's the area in the right tail for my degrees of freedom, which impacts my t distribution. And then there's my little graph, right? This one's on the right tail where my z isn't. that makes that impact for us, 1.341. I just want to make sure that you see the difference as you're going back through here. So if I'm looking at T here of 0.10 with 15 degrees of freedom, that would be 1.341. And you literally just get that from the chart. All right, that's what that is. All right, so the area that we're looking for here under the okay, so let me say that again. The area under my curve, shouldn't have put that line there. Because that's, remember, this subscript is always area. This is my area. So the area is 0.10. What we're trying to figure out is what is that T value. And the T value here is 1.341. All right. Okay, with those 15 degrees of freedom, that makes a difference. So let's swing back over here to the chart because I want to point this out real quick. Look at what's happening at the very, very bottom of the chart. What variable do you see? Z. Why do you think that is? As this gets higher and higher degrees of freedom, what do we know? What's that very last characteristic? The law of large numbers. The bigger it is, the closer it gets to normally distributed. This is normally distributed. So if you're saying I've got these huge amounts of numbers here, these great big huge numbers, the bigger they are, the closer it gets to normally distributed, and the chart even reflects that. Okay, right? So this is why whenever you're looking at this, my degrees of freedom, these values here, it goes to, let me make this so you can actually see it. This is 50, 60, 70, 80, and 90. I mean, you could still work with this, but honestly, once you get too big, they're like, we're not messing with this anymore. That's just a Z-score. It's more helpful with these smaller numbers that we have. And notice even here with the chart, it's just skipping by the tens. Because once you start getting up into those great big numbers, it's closer and closer. Look at how these values also make an impact. The bigger these numbers are, see how they're getting to be the same type of values, and it's just getting closer and closer to being normal. All right, that's where that's why, oops, let me scoot it back over here one more. That's where we're talking about with these two. It's, look at what's happening. You're going from negative 7.5 to 7.5. It's getting smaller and smaller, getting closer and closer to my normal. So this works when I have small data sets. That's what this is. Let me even put that note on here. Small data sets. That's its key. All right.